We're in. Okay, hi guys. My name is Omer. This is going to be a low-level talk. I will forgive you for sleeping. All right. You have permission to sleep. But for those of you who are really interested in really digging down to low-level and looking at assembly, this talk is for you. And my love to you guys. So who am I? I'm Omer. I'm an iOS developer at C Group. We have a bunch of apps that we develop. One of them, better-known ones, because there was a Cristiano Ronaldo ad last year. It's called Shopee. It's an e-commerce platform. You guys must have seen that really annoying ad. I saw it a few million times. But Shopee is great. Okay. So you guys check out Shopee. For myself, I'm building a live streaming platform. It's part of our game platform, which is called Garena. But anyways, if you want to talk more about that, talk to me later. Okay, so today we'll be talking about dyld and what happens before your main. Okay, so some of you who only use Swift might ask, what is main? Well, main is this. I don't know if you guys have seen this. Those of you who worked before Swift might have seen this main.m file. Basically, there's a function called main, and basically this is the starting point of your app. Okay, this is where your app starts. Normally, in your UIKit application, you will launch this function. It does some stuff. Okay, it does some magic. Not important. But my basic idea here is, what is iOS doing before your app gets controlled, before your code starts executing? Let's look into that. And some of you might wonder why. It's not really that relevant, or I don't really have to deal with it that much. That's not true. Because how many of you have slow launch times? None of you. Wow. This is a really good crowd. So that is awesome. Because if none of you have slow launch times, you probably want to keep it that way. And this talk is then for you. Okay? For those of you who have slow launch time, this talk is also for you, because this is how you can fix it. And if you're genuinely curious about how the OS works, this talk should also fall for you. So this is my pie chart of the audience for this talk. Okay? I hope this should work. I messed up this one. It turns out most of you guys already don't have slow launches, so this is pretty good. Okay. So today's agenda, we'll be talking about 4 main things today. First of all, we'll dig into macO. macO was mentioned just a little while earlier by another speaker, so we'll dig into a bit more detail on what exactly macO is. We'll dig a bit into virtual memory, so back to your OS class 101, and then we'll talk about dyld and what dyld is doing, and then finally we'll talk about the best part about this whole talk, the practical takeaways, what you can actually learn and use in your projects. But one key idea I want to highlight first before I go into that is the takeaways can change, because iOS evolves every iteration. The way dyld works and internals will evolve. So my main message to you guys is, try to understand the theory part, so that no matter what happens on the iOS front, no matter if the static libraries are faster versus dynamic libraries, etc., that will change. But if you understand the theory and you understand what's going on, that won't change. The fundamentals remain the same. Okay, and we're going to focus on the fundamentals first. All right. Okay, macO. What is macO? How many of you have heard of macO before? Oh, okay, a fair bit. Very good. So macO is exe, basically. So those of you good old Windows guys, if you use Windows, exe is the executable format on Windows, ELF on Linux. macO is the executable format that we use on iOS and macOS, all the Apple platforms. And there's usually 2 types of executables, broadly 2 types of executables. First type of executable is your main app binary. So this will be normally located as a binary file. So when you compile your app, you'll have like a .app folder, right? If you look into that folder, normally, let's say you have an app called foo. Inside there'll be a binary called foo, and that binary is inside this. That binary is just a file, and it uses this format called macO. Okay, so that's one type of macO. Another type of macO is called a dyld, or aka a dynamic library. So let's say you load a bunch of dynamic libraries. Most of you guys probably include the Swift runtime libraries, for example, I live Swift core. This is a dyld. This is also a macO. So the format that these guys have is the same. Okay, just want to highlight that. What about frameworks? Some of you guys might ask, hey, frameworks, what about those? So frameworks are actually just a folder structure. They are a folder structure that contain a dynamic library inside with a bunch of other stuff. So it's a nice way of organizing a library, because you can then put your headers in this subfolder. You can define a module map if you're using Swift, which you should be, and there's an info plist inside. But basic idea I want to highlight here is that the binary is inside here. Okay? So there is a binary dylib inside. Okay, so let's dig a bit deeper into Mach-O. So what exactly is inside Mach-O? So Mach-O files are divided into segments, okay? Makes sense. You want to organize your file a bit, I guess. So there's 3 types of segments inside Mach-O. There's a text segment, a data segment, and a linked edit segment. And we'll talk a bit more on these in a bit more detail. But one thing I want to highlight is that all these segments, they're of a particular size, and that size usually is a multiple of your page size. What is page size? Well, I don't know most of you guys, you write software, but you know most software runs on hardware, right? I guess most of you know that. So hardware normally operates in quite a different way than what you'd expect. So normally when you talk about memory, the way memory hardware works is it will fetch stuff from your RAM in pages. When you move stuff from your disk to your caches, from your caches to your memory, it'll always be in pages. So you have a page size for your CPU architecture. So that's why you try to memory align everything to be close to that page size so that you get best performance. Once again, because your code that runs on real hardware, it doesn't run in some abstract machine that you might think it does. Okay? All right, so let's look a bit deeper into these segments. What are these segments for, and why do we have them? So the text segment, right, is where you have a few things defined. Most important thing inside the text segment is the Mach-O header. So the Mach-O header basically contains information about the Mach-O file itself. So it'll tell you where all the segments are, what libraries to load, etc. We'll dig into this a bit more detail in a bit. The text segment also contains all your code. So all that beautiful, beautiful code that you wrote using all the design patterns from the Gang of 4, it'll all be compiled into nice readable assembly, and all of it will be inside your text segment. Okay? Also, your read-only constants will also be inside your text segment. And if you notice, everything inside text segment is immutable. You cannot change it. So when you load this text segment, you will load it with a read and executable permission only. You don't need to write it. So these are the permissions that are available when you load the segment. It's only read and execute, no writing. Okay? Next thing is your data segment. So data segment basically contains everything that you can read and write to, but can't execute. Okay? This is stuff like all your global variables, which as we learned in an earlier talk, you probably shouldn't be using, but hey, you still have them. All your static variables, etc. All this is in your data segment. And finally, you have this funny segment you might not have heard of. It's called the linked edit segment. The linked edit segment basically contains some metadata that dyld will use later on. Okay? So far, so clear. In short summary, Mach-O contains 3 segments with different permissions. Okay? Cool, we're done. Let's look at Mach-O headers. Okay? Mach-O headers are, well, like I described to you, they describe what this Mach-O is going to be like. They contain metadata about the binary. So things like your section names and addresses. Like I mentioned, there are 3 sections just now, right? But you don't know how big they are. You want to know how big is your text segment, how big is your data segment, etc. That information is inside the Mach-O, inside the Mach-O header. Okay? Also, it includes all your library dependencies. So if you're wondering, for example, when you start your app, how does your app binary know that it needs to load, for example, Core Foundation, or it needs to load core data if you're still using core data like we do? We use core data. We still use core data. It's nothing to be ashamed about. Okay, so if you want to know where this information is, it's all inside the Mach-O header. And obviously, the most important thing your Mach-O header needs to have is your main function address. So you need to know where in your binary is your main function located, and this is also inside your Mach-O header. And finally, your code signature, because yay, we have code signed binaries, because we don't have malware like Android, yay. So code signature is inside there as well. Okay, so I'm going to show you something very scary now. I know half of you will probably be scared to death. Boom, this is what the Mach-O header looks like, okay? So if you ignore the addresses, just look at, it's actually quite readable, I think. So basically, Mach-O header is described as a bunch of load commands. Okay? So the header has a bunch of load commands. The load commands are load segment. So this load segment 64 means load a 64-bit segment from this address to this address, and this segment will be my page 0. I'll talk more about page 0 later on. Then it says, oh, this memory address, so this memory address is text, this memory address is data, etc., etc. So you can see it's defining all the segments that I described earlier, and it's telling you what their addresses are. These are addresses inside the binary, okay? It's also telling you what is the main entry point. So it tells you, okay, the main function is located at this address. It's also telling you, oh, I also depend on this other dylib called Core Foundation, which most of us usually depend upon, unless you are doing something really funny. I'll be very surprised if you don't depend on this. And normally this will include a lot of other dylibs that you'll probably load. Okay? Okay, so now that you all are experts in Mako, we can pause the Mako, and just remember that Mako has segments, got this nice fancy header, all the dependencies are there. Let's pause that for now, and let's take an OS class into virtual memory. Okay, everyone's favorite topic. So why am I talking about virtual memory? It'll be clear to you guys in a bit, but until that, here's a very famous quote by David Wheeler: all problems in computer science can be solved by another level of indirection. All you need to do is add one more level of abstraction, and you can solve almost anything. Okay? So virtual memory. What is the problem virtual memory is trying to solve? Once again, hardware. It's always about hardware. Hardware is a real platform. So, oh hey. Okay, so the idea here is your process has some memory that the OS will give you. Okay, the OS will say, okay, process A, you have memory from this range to this range. How do you map that to the actual physical hardware memory? Because your RAM is not going to be, infinitely sized. You need some mapping somewhere, right? Now this mapping normally is maintained in the kernel, and this mapping from logical memory to physical memory is called virtual memory. Very simple, nothing complicated. Okay, but virtual memory allows you to implement some very powerful features, and those features, because it's a mapping, you can actually have addresses that don't point to a real address in your RAM at all, and that's pretty magical, because then you can do some kind of really smart features. For example, what you can do is, let's say, to process A, this memory address is something else. Process B is something else, but actually they point to the same address in your RAM. And this way is one way you can get RAM sharing, because let's say you know that this thing in memory is the same, it never gets mutated, you can share RAM between processes this way. This is one way in which you can use this layer of abstraction. Another way you can do this, and this is something quite magical, I learned this only recently, is memory mapping. So you guys might have heard of memory mapping, or mmap. Basically, the idea is that you will map some address to some data in a file. You will say that this address from this memory address to this address should map to my file data from this offset to this offset, and the kernel will load your file from that offset to that offset lazily on demand. And this way, it doesn't need to load the whole file. It only needs to load that segment you're interested in, and it will just put those stuff in memory. And this is heavily used by dyld, and we'll discuss a bit more about it later on. So another big thing is copyonwrite. So I think most of you would understand copyonwrite because most of you are good people who use Swift and use Swift arrays. Swift arrays have copyonwrite, So when you make a mutable array, and if you mutate it and someone else loads the array also, it'll create a copy of that array. This is called copyonwrite. And normally, copyonwrite also exists in your RAM. So if you have some pages that you mutated in your RAM that become dirty, you can then create a copy, basically, of those pages. Okay, this is copyonwrite. Okay, just so I guess I lost everyone just now, but I'll just give a very quick example of what's going on. So let's say that we are using dyld now. Here is my core data.dylib, because I use core data here because I know this is a hotly debated library, and everyone loves core data, lol. So let's see what's going to happen when dyld loads this library. Okay, so the first thing we're going to do is we're going to load the header. So what dyld is going to do is it's going to say, okay, I'm going to memory map this is my process memory. I want to memory map this address range, this page, basically, to my header. So imagine these are all your pages in memory. I only have 5 pages in memory. I want to load the header page inside my memory. So what's going to do is it's going to ask the kernel, hey, do this for me, and then it's going to access it. That'll file a kernel fault, and the kernel will basically load the header. So to process one point of view, this memory address has the header page inside. The RAM's point of view is actually this address. In reality, it's this address. And the header's been loaded. Everything's good. Similarly, I'm going to load the linked edit section because I need to read some metadata about what I'm going to do next. And then I'll load the data segment because I want to actually do some changes to data segment. This is a hint what's going to happen next. So dyld will actually do some changes to your binary before it starts to execute your code. So it will load the data segment, and it will load at this address once again. And now what it wants to do, it needs to fix this data segment. So it needs to change the data segment. So now it changes this data segment, and this page is marked dirty in the RAM. What that means is if someone else tries to access this same memory, it should create a copy, okay? Because you don't want the same kind of mutations to be shared amongst processes, because these are supposed to be unique by process, okay? So what happens if another process loads this dylib? Once again, process will go through the same thing, load header, load data, load linked edit. But like I mentioned earlier, it'll create a copy of the data segment, and then it will just mutate this data segment, data page, not this one. So overall, the reason I want to highlight this is that if you do this in a naive way, like say you just malloc 5 pages of memory, and then you load the entire dylib of core data, which let's say you can believe it's 5 pages, you will have a total of 10 dirty pages if you do this in 2 processes. But with memory mapping, you can save those number of pages by lazily loading segments when you need them, and you only load those parts. And because you have different permissions for different segments, you can do some reusing. So in this case, for example, both processes will actually share the header page and will share the linked edit page. So we only have 2 dirty pages. We share a lot of memory. And that's the only thing I want to highlight to you guys. This is actually how system frameworks will load. And that's why system frameworks can be quite fast, because a lot of this data is already shared. And that's why usually you can load it quite fast. Okay? So another point I want to highlight is security. We had a security talk earlier, and I think those of you who are interested in this will love this part. So for security purposes, macOS images are loaded at random addresses. What that means is that when your process starts, right, you do not know what address it will start at beforehand. So let's say, just imagine this for a bit. You compile, the compiler will compile your code, right? It has all these pointers in your code that are addresses, right? So you know that, for example, you have a string, you have a global variable called iOS conf, because you're writing an iOS conf app, and as Peter said, global variables are okay now. So you have iOS conf as a global variable. It has some address in your code, right? So if you don't know where your program is going to start from, how do you know the address beforehand? You don't, right? You somehow need to fix this data up. And one of the tricky things is that address will be random. And this, every time you run the program, it'll be random. This is called ASLR, Address Space Layout Randomization. And this is there for security purposes. The reason why you do this is to prevent some kind of buffer overflow attacks. Because if you don't do this, it becomes very easy to hack your binary. Okay? We won't go into that, sadly. Okay, the other thing we need to do is we also need to do code signature. Okay, so how does code signature work? 101, the simplest way to describe it is, imagine you verify your entire binary. So you will basically run some hash on your whole binary, and you can verify that hash later on. The problem is, like I described to you, you are loading everything page by page. So how do you do code signatures now? Because it's page by page, right? The hashes of the whole binary. So they do something quite smart. They will actually hash each page's content. And this hash will be verified when you do a page in of that page. That's how code signature will work over here. Okay? All right, so boring part over. Now we come to the fun part, okay? So dyld. Now, how does dyld come into the picture? Okay, now imagine in the good old days, before you had shared libraries, right? Before we had all this complex stuff. We're talking about 1980s, 1990s, when life was dangerous, life was fun. All you need to do to launch a process is just set your program counter register to the main function, right? And that's it. So the kernel will map your application to some address space. So like I mentioned, because of ASLR, the start of your address is random, so you don't know where it's going to start. And another thing to note is the lower bytes from 0 to whatever random address you're starting at, this area is marked as inaccessible. So normally, the reason for doing this is actually to catch null pointer exceptions. So how many of you guys have had exec bad access before? Yay! Okay, do you know why it happens? Or do you know how does the runtime know it's a bad access? It's because your pointer hit in this page. So basically, what happens is this page is not mapped to any real RAM. It's just a logical thing. So what it does, the kernel does, is if it sees a pointer in this address range, it will fire your exception handler, and it'll crash your app, basically. So that's how exception handling works. And this is the reason why we need this. We reserve this part for this, to keep this kind of null pointer exception checking. Okay? It also catches other bugs, like let's say you have a 32-bit pointer, and then you somehow cast it to a 64-bit pointer because you're using C and because you like to live life dangerously. This will also be caught in this exception because the page 0 is 4 gigabytes in size. Okay. All right, so in the old days, like I mentioned, you can just set this program counter register to main, and you can start executing your code already. That's it. Don't have to do anything because you don't have any shared libraries in the good old days. Sadly now, you have dylibs that you have to load before your application can run. So how can we solve this problem? So this is where dyld comes in. So dyld, so whenever you start your app is not the one starting actually, or your code is not executing. The first thing that will execute is dyld main. So kernel will actually load dyld at some random address in your logical address space, and dyld itself has its own text segment, data segment, and its own linked edit segment. And dyld's job is basically to load and set up all these dylibs for us. Okay, that's what dyld will do for you. So what does dyld have to do? It has to do quite a few things actually. So it has to load all your dependencies in memory, and it has to do this recursively because you depend on library A, but library A depends on library B depends on library C, and library C might depend on library A again. Like you'll have this graph of dependencies that needs to be resolved, and all these libraries need to be loaded in memory. So dyld has to do all that. It has to do this thing called rebasing your dylib images. I'll explain this in more detail later on. It has to do this other thing called binding. I'll talk about that in a bit also. And it has to prepare all your runtime to make sure your runtime is ready. I'll talk about this again in more detail in a bit. And then it has to run all your initializers. Woo, that's a lot of things. So let's go into a bit more detail. And this is either the most interesting part of the talk or the most boring part of the talk, depending on whether you're interested in the low levels. But OK, let's talk about loading dylibs. How do you load a dylib? Like I mentioned, a dylib is just a macro file. And I've described what the macro file looks like. So you just have to parse the macro header, find the dependencies. And remember just now I showed you guys a macro header? This is what the macro header looks like, right? So there'll be a few little dylibs inside the macro. There'll be, for example, core foundation, core data, etc. So you need to parse this header so you know what libraries to load. Then you find the library file on the file system, because all of these are actually files in the file system. Then you parse those files and you validate the dylibs again. Once you load a dylib, you need to go through all the segments that are described in the header once again, and you need to memory map those segments onto real memory. So you memory map the text segment onto some address, the data segment on some address, etc., etc. This part is simple. Okay. Yeah, like I mentioned, you memory map all the segments one by one. Okay. And you need to do this recursively for all the dependencies, and you need to register the code signature. So this part is still easy. So overall, in the end, after you are done with this step, you will have a bunch of dylibs loaded into your program's address space. So in this application, foo, which is a brilliant name for an application, you'll have A dependency and B dependency. Both of these dylibs are loaded. Okay. Normally, for a typical app, this can be anywhere between 1 to 400 dylibs. Now, I mean, that's a lot of work, right? 400. You need to do all this work for 400 libraries. That can add up quite a bit. Thankfully, most of them are OS dylibs. So the OS will actually cache a lot of this information, so you don't have to do a lot of this work again. But it's your libraries that you have to worry about. And that brings us on a fascinating debate on dynamic versus static libs that we'll cover later on. Okay? All right, so the second part that we need to do, remember I mentioned earlier on that dyld has to fix your binaries, and I give you a hint of that by explaining that your pointers need to be fixed. So let's talk a bit about that. So like I mentioned, when your code is compiled, it does not know what are the addresses of all these dynamically loaded functions. Like you call nslog. Where is nslog? At compile time, you don't know, right? Because nslog, I mean, how do I know where address of nslog is? Especially with ASLR, I don't even know what it could be beforehand. It's going to be random. So I don't know. I just pointed to some null value. Hopefully, you'll fix it for me later on. Similarly, for constants and functions inside your own binary, let's say you have a function called hello world inside your application. Because of ASLR, you don't know where the address of hello world is because it's been moved because of ASLR, right? And it moves every time. So you need to fix this also. And one issue with this is, remember, you have code signing on your text segment. That means you cannot modify your text segment because your text segment is read-only, like we said. So you can't actually modify the code, but you still need to fix the pointers somehow. So we'll dig into that on how we do that in a bit. So let's talk about rebasing. That's the first step that we need to do. So in rebasing, the way rebasing works is your linked edit section, which is the last segment that was mysterious and we didn't talk about it yet. The linked edit section is constructed by your compiler, and it knows where all the pointers are located, and it knows their addresses. So what the compiler will do is that it will go through all these pointers, and it will shift them to the correct location based on your application's start address. because at runtime you already know where the address is. And to do this, you need to read and write all your data pages, go through all your pointers, and fix them, which will cause your pages to become dirty, will require copy-on-writes. So this process can be expensive in terms of I/O. Let's look at a concrete example for this. And the kernel will do some, the kernel can improve the I/O a bit by doing some prefetching. Okay, so let's say we have a function, C function, sorry, hello iOS conf, okay? And then I call this function hello iOS conf, okay? In the function, I'm just calling nslog with hey guys. So what does this function look like in assembly? Okay, let's look at it in a bit. So if you look at the place where hello iOS conf is called, it's actually, and there is an instruction in your architecture, whether you're using ARM or using x86 64, there will be an instruction to do a function call. Normally it's called call something, okay? And for call, you need to pass it an address. You need to pass it the address of the function that you're calling. So in this case, we know this address is hello world because this comment says this is hello world. And if we scroll up the binary, we see, okay, hello world starts from this address, okay? So we know this pointer exists. This is in our code, right? What we need to do is we need to change this because now we have ASLR, this address may not be correct anymore. So we need to fix this address somehow and shift it by whatever random address our process got shifted by. This process is called rebasing, okay? We'll look into a bit more detail on how it does that in a bit. Another process is called binding. So you will be calling other library functions, right? You have to. You can't just live in a shell. So you will definitely be using nslog or oslog. Or you will be using malloc, even though you don't know you're using malloc. You are using malloc. You use ObjectiveC, you're using malloc, definitely. You're using Swift classes, you are using malloc. So when you load all your dependent libraries, dyld has to search for all these function calls. So there's actually a string called _malloc inside your binary that is unresolved. And what dyld will do is, once it loads all the dependent libraries, it will load all the symbol tables of those libraries and will find the addresses of these functions. Naturally, with 400 dylibs, this can be expensive. And this can be quite computationally complex, so this process can take a while, okay? I just want to highlight this is expensive, okay? Okay, but so how does this work? Since I can't change my code segment, the way this works, and I'm sure I'm going to show you some more assembly, so please get scared. The way this works is, imagine that I have some nslog function call, right? So I have a function call, and it's loading ns. This is actually nslog. The fact is, no, it's actually not nslog. Okay? This address actually is a stub for nslog. What that means is we add another layer of abstraction here. What we do is we actually, instead of pointing to the function, we point to some pointer inside our data segment instead. So this actually pointing to this pointer in my data segment, and because this pointer is in my data segment, I can change it because this data segment is writable. And what dyld will do at runtime is it will find this data pointer and will change its address to point to the real nslog. That's how your data fix-ups will happen. And the style of programming, of generating code in this way where you generate stubs, this is called position-independent code gen, or PIC. Okay? All right. Lastly, we need to set up the Objective-C runtime. So everyone here loves Objective-C, especially Tim, I think. So for Objective-C, you know, all Objective-C class definitions need to be registered. You know why? Because you know you can construct a class from a string, right? You can call ns class from string, and you pass it the string of the class you want to load, and that works beautifully. And that's a beautiful feature, especially for people who love reverse engineering and who love hacking into other people's apps. That's beautiful. So, but how does that work? It works because Objective-C runtime has a mapping of all the string class names to their actual class addresses. And this table is built by dyld before your app can launch. This is called setting up the Objective-C runtime. This also includes some other things, like let's say you have a category on UI view. How do you know, so if you have a category on UI view and you add some new methods to UI view, how do you know those methods are there? That information needs to be inserted into UI view's method list, which is maintained by the Objective-C runtime. This is also done at this time. And you have selector, uniquing, and a bunch of other things. Finally, you will run your static initializers. So at this point, you know there's this thing on Objective-C called +load. You might have thought of using it, but please don't. It's deprecated now. Basically, your load methods will run over here. I can see the Swift guys are yawning at this point, which is good, because for Swift people, you don't need to worry about this. But for those of you still using Objective-C, don't use this, please. Basically, because this will be called before your main. And you'll also run your C++ initializers, and all this will be run bottoms up because you might be dependent on some code from your dylibs at this point. Okay, whew. Finally, after all this is done, your main will execute. So that was a lot of work, okay? Now we're going to move on to the juicy part of this talk, the highly, hotly debated practical tips section, okay? Okay, but before I go on, I want to summarize everything I said just now. So, just to repeat, Mako uses this, Mako is this format, has these kind of segments. dyld needs to parse and load all your dependencies, which is a lot of work. It needs to fix all the pointers in your dylibs. It means it needs to rebase, bind, and set up your runtime. It needs to run the static initializers and the plus load methods. And then it will call main. This is the one slide summary of my entire talk, okay? So this is all the stuff that dyld has to do. TLDR, a lot of stuff, okay, before your main is run. Okay, so obviously the most important and obvious tip is don't use plus load because it's going to run before your main. If you're doing anything inside plus load, please don't, or delay it, or use plus initialize instead, which will be loaded after your main and will be loaded in lazily. Okay, so normally, if you want to profile and optimize your startup time, obviously the thing you have to do is you have to profile it. And you have to profile in different cases. You need to profile for warm launches, cold launches, etc. And make sure whatever changes you do, you profile every time. Okay? So dyld helps you with this. dyld has this very nice environment variable that you can set. It's called print statistics. You set this environment variable to 1, and it will give you a summary of everything that happens before your main is run. In this case, this is terrible. 1.5 seconds is super bad. That's damn slow. Ideally, Apple says you should run your main within 400 milliseconds, which is quite hard, actually. But over here, you can also see the steps. So you can see I didn't make any shit up. All this shit is real. So dyld loading, dylib loading time, rebase binding time, setup time, initializer time, all these times are there. These are the 4 steps that I talked about. And you can see their times and their summaries, what's taking the most time. In my case, it's initializers. But I promise I don't have plus load. So the reason why this is taking so long is because I ran this with the debug build. So there's a lot of extra libraries that will be added when you do debugging. For example, your main thread checker dylib. This is the dylib that will check. You know, when you run a debug session, you get these warnings that tell you when your main thread is being called in a non-main. You call shit that depends on main thread, but you call it a non-main thread. This is the library that checks for that. It only runs when you're running debugging. Similarly for a bunch of other libraries here. Anyways, now another hot topic is, should you profile for warm launches or cold launches? So Apple has 3 WWDC videos about optimizing your app launch. In the first video, they said you should profile only for cold launches. In the second one, they said you should profile for warm launches. In the third one, they didn't mention exactly. So my point is that no matter what, the reason why Apple had different advice is because they changed the implementation of dyld, and they change it every year. They keep optimizing the shit out of it because it's expensive and it's running before every app launch. So if they optimize, everyone wins. But my advice is profile for both. By cold launches, I mean you reboot your phone and then you launch. The reason is that it will flush out any OS caches that may have been built, and it will help you get a good idea of how it seems to the user if they use your app after a very long time. Okay? All right, my favorite topic, and I guess most of you are interested in this, static versus dynamic libraries. Okay, so for system libraries, dynamic libraries make a lot of sense because you save on app size. If you were using static libraries for system libraries, you will have to ship all those system libraries you depend upon with your application, and that can really, really boost your app size. And you don't want to do that. You don't want to duplicate copies of those common libraries inside all the apps you use. Also, system libraries are very aggressively cached, so you don't need to worry about them too much. And therefore, they're quite fast. However, for your libraries, you need to understand that if you use a lot of dynamic frameworks, which is, usually splitting up the code into frameworks is a pretty good idea, but if you have a lot of them, you remember dyld has to do all this work that I talked about. Although it's getting better over time, because dyld 3 has some improvements, it's still going to be quite slow. So in terms of startup performance, static libraries will always be better, because static libraries don't need to do all this parsing, loading work. They still need to fix pointers, but static libraries are already in your binaries, so the amount of work you have to do is a lot lesser. And most of the work, linking work, is already done at compile time, and compiler can do some better optimizations, like more inlining if you use static linking. And you can optimize away unused code. However, static libs are not a silver bullet. And if you have extensions, for example, then you might have a lot of disk usage because your static libs will be copied in your app extension binary and your main executable. So you need to be careful about that. And the static libraries are a bit hard to use with current tooling because if you have resources, you need to generate your resource bundles, etc. You can talk more to me about this later on. Just a quick use case I want to show. So Shopee is one of our apps. You guys know about Shopee. We saved around 40% of our pre-main time by shifting to static libraries. Just want to highlight that. And this can be quite considerable depending on your application. Oh, one more thing. If you're using macOS and you can change the header a bit, you can do quite a bit of reverse engineering. So which is quite fun. Like you can use Pokemon Go, inject your own library inside. It's quite fun. Talk more to me about that later on. Okay, conclusion. dyld runs before your app can start, does a bunch of stuff, fixes all your libraries, and you can improve this by using fewer dynamic libraries or by shifting to static libs. But your mileage may vary. Okay, that's it. That's all I have. If you guys have any questions, let me know.